4.3, rotations. Essential question, how can you rotate a figure in a coordinate plane? How can you identify rotational symmetry? Here's the definition of a rotation. There are two parts to the rotation description. One of the things that you need to understand is we rotate from the center of rotation, and we have an angle of rotation. Those are the two things that help us rotate. Let's give you a feel for a rotation. Right here is the center of rotation, and here is the angle, and if I move the angle, you can see how it rotates. If I can go ahead and change the center of rotation, and again we are supposed to go counterclockwise, so we go in this direction. You can see how it's moving, transforming. Let me go ahead and put the center of rotation right here at the edge of the rocket ship here. And you can see as I rotate, that point, the center of rotation doesn't change because it's part of the point of the figure. And so that's the feel for what a rotation is doing. So Q is, when Q is not the center of rotation, like in this example, then we know these lengths right here have to be the same. That's what it's saying right here. And we have to have an angle description from here to here. And again, the second part of the definition is if Q happens to be the center of rotation, so if it happens to be right here, then Q doesn't change. It's the point, the pre-image and the image will be the same point. All right, let's take a look at finding the image from the pre-image. Here's B, and here's the center of rotation. I'm going to take a protractor, and the protractor already has 120 degrees measured in here. And what I'm going to do is I'm going to take B and I'm going to rotate it over here. Remember, this length PB and PB prime are exactly the same, and I've rotated 120 degrees, and this is the pre-image, this is the image. Now I'm going to do that for C. Now here's C. Here's the pre-image, and I want to rotate it to C prime. Again, I'm going to need to use a protractor. And here I'm going to, this length and this length are exactly the same, and it's going to rotate. And that'll be the image. This is going to happen for A prime as well. And when I join A prime, B prime, and C prime, you see I get this right triangle, just like I had over here. All right, let's take a look at the coordinate rules for rotations about the origin. So if we take a point and we rotate it around the origin 90 degrees, this is the rule that we have. For 180 degrees, this is the rule. Notice all it's doing is changing the sign of X and Y. And for 270 degrees, this is the rule. Again, we turn counterclockwise unless otherwise stated. Let's take a look at a problem in which we go ahead and do a rotation. Now we're doing a 270 degree rotation, so I want to write the rule to remind me what to do. A 270 degree rotation is y, comma, opposite of x. So r prime will be, I'm going to take my y, which is 1, take my x and change its sign. S prime will be 1, negative 5. T prime is going to be negative 3, negative 5. And then U is going to be negative 1, negative 2. Now let me go ahead and plot these points. 1, negative 3. 1, negative 5. Negative 3, negative 5. Negative 1, negative. Okay, I can see I have some points that are wrong. Let me go back. Okay, how about 1, negative 3, 1, negative 5, negative 3, negative 5, negative 1, negative 2. And I'm going to go ahead and join them. And you can get the feel of this thing turning 90, 180, and then 270. Okay, a rotation is a rigid motion. So when we move the points in a rotation, all the sides will stay the same, congruent to each other from pre-image to image, and all the angle measures will stay the same from pre-image to image. Let's take a look at going through a composition where we go through two transformations. Now, a reflection is going to be, this is a rule for a reflection, x comma y for the y-axis, and in the y-axis it's the x's that change, so that's the rule. And rotating 90 degrees about the origin, that rule is the origin is opposite of y comma x. So in going through the reflection, this will be r prime, and r prime will be opposite of 1 comma negative 3, and s prime will be negative 2 comma negative 6. So let's go over here and graph it. Negative 1, negative 3, negative 2, negative 6. So this is r prime, s prime. Okay, now what we want to do is we want to go through another transformation, and this transformation will be r double prime, which means I'm going to take my y and change its sign, and then x, leave it alone and put it in that spot. S double prime, the rule is take the opposite of y and then leave your x alone. Let's go ahead and graph this, and this is going to be 3, negative 1 right here, and 6, negative 2. So this is r double prime and then s double prime. So you can see the look of turning 90 degrees here. So there was a reflection and then a rotation. Okay, let's go ahead and stop the screencast, see if you can do this problem, and I will show the answer. And here's the answer. You can see that I did it one at a time. I did a translation, and it was just moving over 2 units to the left and 1 unit down. And then I went and rotated about the origin, so you can see this turning effect that's here, turning effect like that. Okay, stop the screencast and see if you can do this one. And let's take a look at the answer. You can see that I'm going through a 180 degree rotation about the origin. So this is going to turn from here all the way here. That's the prime. And then afterwards, I'm going to reflect across the x-axis. And reflecting across the x-axis will give you that. Okay, let's take a look at rotational symmetry. Rotational symmetry is when the figure can be mapped onto itself by rotation of 180 degrees or less about the center of the figure. So you can see in these pinwheels right here, if you turn 45 degrees, it doesn't look like the original figure. But if you turn 90 degrees, then the pinwheel looks like the same as it was in the beginning. And if you turn 180 degrees, that happens. Let's see, I have a little demonstration here on rotational symmetry. Let's go ahead, and this slider here will start turning. And we want to stop when it looks like one of the figures lines up. There we go. It looks like at 72 degrees, the pentagon matches onto itself. Let's keep going. I'm getting to about 120 degrees, and you can see this matches onto itself. And when I get to 144 degrees, it looks like the pentagon has matched onto itself. And then when I get to 180, it looks like this matches onto itself and the parallelogram matches onto itself. So that's what we call rotational symmetry. You're going to, and if you can match something up in 180 degrees, we call it point symmetry. Okay, so let's take a look at these figures. Does the figure have rotational symmetry? And for the first one, we just saw a demonstration with a parallelogram, and the answer is yes. And if so, describe any rotations, and that is 180 degrees. Now here on the octagon, this is what I like to do with an octagon. The center of rotation is in the center here. And then I'm going to divide it up like this, like a pizza. And I can see I have 8 slices. Okay, so if you divide 8 into 360, you're going to get 4, that's 32, 405. So each one of these angles is 45 degrees. So you're going to have to, we're going to say yes. If you turn 45 degrees, you're going to see the octagon turn onto itself. And then 90 multiples of 45, 90, 135, and then 180. Now the trapezoid here, it has no rotational symmetry. It actually takes the whole 360 degrees to map onto itself. And remember, the definition says 180 degrees or less. Okay, what about this one? Again, put a center right here. I like to go ahead and draw diagonals because this kind of helps me. And you can see that it's going to, if you just turn 90 degrees, this shorter is not going to match perfectly. So this is going to have to take 180 degrees. So this is yes, but it'll take 180 degrees to do that. Now here, it looks like you're going to be able to get away with 90 degrees for this to match onto that. So we're going to say yes, this will be 90 degrees and 180 degrees. And the triangle, no rotational symmetry. You put a center right here or here or somewhere there. It's going to take 360 degrees to do that. And this is the end of the screencast.